Alrighty, so tonight we're going to be talking about heating and cooling curves, and we're going to start out with a bit of a review of heat and then add some new stuff to it. So, if you can think back to the beginning of the year when we started talking about heat, we actually used an equation Q equals mc delta T, where Q stood for heat or energy, M was mass, C was specific heat, and delta T was change in temperature. And we used this and we were able to calculate how much energy was required to raise a specific mass of a substance by a certain change in temperature. Now, we did this kind of by like heating up water or something like that. But the thing is we didn't take it much further, and there's a lot further to go with it, because not only are we able to warm things up, but we can actually make substances undergo phase changes. But it takes energy to undergo these phase changes, just like it takes energy to heat up something and get the molecules moving. A phase change is exactly that. It's getting the molecules to move and change and move further away from each other or move closer together. And so it takes energy to do that. And so we need a new equation in order to do that. And that new equation is called Q equals N delta H, where Q, again, still equals heat, but N now equals moles. And obviously this is why we didn't talk about this back in Unit 1, because we had no idea what a mole was. And then delta H is going to equal something new that we haven't heard of before, called enthalpy. And here it's going to be the enthalpy of fusion or vaporization, depending on when we're talking about, and we'll kind of get into that in a little bit. So again, there's going to be two equations, only one of them's new. The old one, Q equals mc delta T, and now the new one, Q equals N delta H. So MCAT and however you want to think about it. So, when we talk about heat, a lot of the times we talk about heating and cooling curves because it's the best way to kind of visualize what's going on here. And so a heating and cooling curve is a measure of a change in temperature against energy. And we're mostly going to be talking about water here. And so I've actually put in the two temperature changes where phase changes occur for water of 0 and 100 degrees Celsius. Now this graph shows us a lot, actually. It shows us the different phases and the different phase changes that are occurring. So this first phase here, where we've got that first red angled line, that is going to be when the substance is a solid. And you can see that the temperature is increasing because we can warm up a solid. For instance, with water, this is going to be solid ice. This next sloped part, the center, is our liquid phase. So this is talking about liquid water. And then finally, our gas phase. And so you can see that we've got these three different phases, solid, liquid, and gas, and they are all undergoing a temperature change. Now you can go up or down the curve depending on what you're wanting to do. If you're going up the curve, this is called a heating curve, because we're taking a solid to a liquid and melting it, and we're taking a liquid and boiling it into a gas. That's going up the curve. We're putting in heat. We're increasing the temperature. You can also go down the curve, and that's now a cooling curve, where we're taking a gas and condensing it back into a liquid, and then we're taking a liquid and freezing it into a solid. So you can go either way. Now, if you have a change in temperature, you're going to be using the equation from those first equations that we looked at, Q equals mc delta T, because obviously the delta T stands for change in temperature. So that's going to be those red sloping lines. And what Q equals mc delta T means is that it's saying that all the energy that you're putting in is actually going into raising the temperature of the substance. So it's going to be those sloped lines where you've got a vertical change in temperature. That's why they have a slope. And so Q is going to be equal to mc delta T, change in temperature. You've got an increase in your slope. If you're changing the phase, you're going to use that new equation, Q equals N delta H. And here, all the energy is going into changing the phase. So here, as we go across our x-axis and we put more and more energy in, our temperature is no longer changing. Instead, we're just undergoing a phase change where we're physically changing from a solid into a liquid. And so we're going to use that Q equals N delta H. So the flat parts of the lines are phase changes, and we use Q equals N delta H. Now, that delta H is talking about these different phase changes. And if we're going from solid into liquid, that purple to green stage, that's going to be called the delta H of fusion, or delta H fuge. and that's talking about fusion, solid into liquid. If we're talking about our other phase change going from green to orange, that's going to be the delta H of vaporization. You are vaporizing, you're going from liquid to gas. Okay? So that is what we've got going on here. We can look and see a lot of information from one really tiny graph. So you might want to take a minute and look at that and really understand it. Perhaps write it down. That might be a good idea. So as you can see, there's a lot of different variables on here that we've got going on. We've got C's, we've got delta H's, we've got delta T's, we've got a lot going on. So let's talk about some of those variables. Some of the common variables that are going to be used with these two heat equations are C and delta H of vaporization and delta H of fusion. C is your specific heat, and then you've got your enthalpy of vaporization and your enthalpy of fusion. The specific heat of water, not only do we have different specific heats for different substances, but the specific heat of water is actually different depending on the phase of the water. The C of ice is 2.03 joules per gram degree Celsius. C of water is 4.18 joules per gram degree Celsius, and C of steam is 1.70 joules per gram degree Celsius. So it's going to be important for you when we're doing these problems to remember what phase you're in so that you can use the appropriate specific heat. Delta H of vaporization is describing the phase change from a liquid to a gas, whereas negative delta H of vaporization describes the phase change from gas to liquid. So liquid to gas is boiling vaporization. Gas to liquid condensing is negative delta H of vaporization. And then you also have delta H of fusion, which is describing the phase change from solid to liquid. And I know that kind of sounds backwards. Fusion, you think of fusing things together, but it actually is solid to liquid. Negative fusion describes going from liquid to back to a solid. Sorry, that should be liquid to solid. Yeah, sorry about that, guys. And I would start over, but I already did that today. I don't want to do it again, I'm not going to lie, sorry. Okay, so let's just go back to that very end. So liquid to a solid, that's going to be negative fusion. Okay? So if you look here, we can see this graphically. It'll make a little bit more sense. You've got your solid, liquid, and gas phase. Delta H of fusion goes from solid to liquid. Delta H of vaporization goes from liquid to gas. Going down the curve, you've got negative vaporization, gas to liquid, negative fusion, liquid to solid. So we're mostly talking about going up the curve, but we can talk about going down the curve, in which case you just have to take those enthalpy values and turn them into negatives. So let's do a problem. So a kind of typical problem we encounter in something like this is a question where it says that a 25-gram piece of ice starts out at negative 38 degrees Celsius and is heated. It melts, and after becoming water is removed from the heat when the water reaches a temperature of 45 degrees Celsius. What amount of heat was required to make this transformation? Now, the trick with solving problems like this is to draw out the problem as a graph, see what's actually happening. So I'm going to put a little cooling curve out here. I'm going to input in my temperatures, okay? I know that I start at negative 38 degrees Celsius. I know that I melt, and this is water, so I know that melting occurs at 0 degrees Celsius. And then I know that I'm going to end it at 45 degrees Celsius. So I'm just going to plug those numbers into my axis. And then I'm going to go ahead and start. So the first thing that I'm going to do is heating. Okay, so the ice starts out at negative 38 degrees Celsius and is heated. Okay, it's going to be heated to 0 degrees Celsius because that's the temperature at which it melts. So I'm going to go from negative 38 to 0. That's going to be a change in temperature. At 0, it melts and now becomes water. So there was some energy input there to melt it. And then after it melted, it's removed from the heat after it reaches a temperature of 45 degrees Celsius. So then we're taking our melted water and we're boiling it, or we're heating it from 0 to 45 degrees Celsius. So we've got another line right there. Now the question is, what amount of heat is required to make this transformation? The thing to remember is that this is a transformation of 3 different segments. The first segment of warming up ice, the next segment of melting ice into water, and then the third segment of warming up the water to 45 degrees Celsius. So we're going to have to do a different calculation for each of those phases and each of those stages. So some important things to remember: this is a solid, this is a liquid, this is the active melting. That's what we've got going on here. The C of ice is 2.03 joules per gram degree Celsius. The specific heat of liquid water is 4.18 joules per gram degree Celsius. Those are two things that we're going to need. We're also going to need the enthalpy of fusion, that whole melting thing. And the enthalpy of fusion for water is 6.01 joules per kilojoules per mole. So that's something that we're going to need for this problem. Now, I'm going to go ahead and calculate the same, do this problem how I would do it. And the first thing I'm going to do is I'm going to calculate the first step of heating up the ice. So I'm going to use Q equals mc delta T, and this is for ice. So the mass is going to be 25 degrees Celsius, my C is going to be 2.08 joules per gram degree Celsius, and my change in temperature, T final minus T initial. T final in this case is going to be 0. That's when I hit my temperature that I can melt at. And my initial temperature is negative 38. If I do a little math there, I get 50.75 joules per degree Celsius, because my grams canceled out, times 38 degrees Celsius. Negative times a negative is a positive. And doing math again, I get 1,928.2 joules. The degrees Celsius is canceled out. So that's how much energy it takes to just do that part of the graph. We still have two other parts. I'm going to stick with the same equation, and I'm going to do my Q equals mc delta T equation again, this time for the water. So I'm going to look at this section of the graph. My mass is still 25 grams. My specific heat is now 4.18 joules per gram degree Celsius. And now my change in temperature, T final is 45 degrees, and T initial is 0. 45 minus 0 degrees Celsius. Do a little math, you get 104.5 joules per degree Celsius times 45 degrees Celsius, leaving us with 4,702.5 joules. And again, that's the energy put into doing this stage of the graph. I still have yet to do the melting. So I know for melting, I'm going to be using Q fusion is equal to N delta H. But I don't know my N and I don't know my delta H. Well, I do know my delta H, but I need to be able to use it. To find out the moles, I'm going to need to get the molecular weight of water. So the molecular weight of water, because I have grams and I know with molecular weight I can get moles. Molecular weight of water is the mass of hydrogen. Sorry, that should be... I'm sorry, guys. This was not my night, apparently. I spent so long, and I wanted this to be so beautiful. Should be 2 waters, or 2 hydrogens, not 2 oxygens. The math is there. Okay. 2 hydrogens and 1 oxygen makes water, so it has a molecular weight of 18.015 grams per mole. And I can take this and plug it into an equation and solve for the moles. Take the grams of water, times it by the molecular weight of water, and I get 1.387732445 moles. Notice how I'm not rounding yet because we don't round until the very, very end. So if I plug that in my equation for N and multiply that by the delta H of fusion, I get 8.3402719996 kilojoules. But all of my other units are in joules, so I want to convert this into joules. So I'm going to divide by 1 times 10 to the negative 3, which gives me 8,340.271996 joules. And that's the energy that's put into this melting stage. So the question, though, asks about what's the heat required to make this transformation. So what do we have to do there? All we have to do is, I want to make this entire transformation, all I have to do is add up each segment. So Q is going to be equal to the energy to warm up the ice, plus the energy to warm up the water, plus the energy to melt the ice into water, and I get 14,970.972 joules, or 1.5 times 10 to the 4 joules, rounding to the correct number of sig figs. So you can see that these problems would actually probably take a while to solve. There's a bunch of different steps to them. So we're going to do some problems, and we'll do some practice tomorrow going both up and down the curve and looking at how all of this works. So come in ready to go. Thanks, guys. I will be able to do this, I promise. Where did it go? There it is. Bye.